right, so now let's go further and look at question 9. And this states, suppose f of x is the sum of a power series with radius of convergence r. And then part A, we're asked, how do you differentiate f? And what is the radius of convergence of the series for f prime, or the derivative of f? And then B, how do you integrate f? And then we're asked, what is the radius of convergence of the series for the integral f of x dx? Alright, so now let's take a look at the solution. And here, so we're going to look at derivative. Basically, you're differentiating or integrating the power series. So that's what we're looking at. And so the solution for both parts A and B, recall from my earlier video. And this is representations of functions as power series. And here is that differentiating theorem and integrating theorem. So this applies for both, because you have the first one is derivative, second one is integral. So if the power series, written in general form, summation of Cn, C subscript n, times x minus a to the power of n has radius of convergence r greater than 0, so that's it has a radius of convergence, then the function f defined by f of x equals to c0 plus c1 times x minus a plus c2 x minus a squared plus etc. equals this right here. This is just a power series, so summation from n equals 0 to infinity of Cn x minus a to the power of n is differentiable and therefore continuous. Yes, you can take the derivative and it's continuous on the interval a minus r to a plus r is open bracket, because it doesn't have to be continuous or differentiable at the endpoints, but as long as in between that it does. So yeah, this may or may not be continuous at the endpoints or differentiable, but at the in between it is. And what we'll have is, so here's the theorem. So if you have the power series and its radius of convergence r, and then the derivative is just equal to f prime of x equals to c1. So this one goes to 0. This goes to 0. Yeah, here, pen's working now. So this goes to 0 when you take the derivative, because it's just a constant. And now this part right here, c1 x minus a, derivative of x is just 1. And in this case, derivative of x minus a is also just 1. So then this would vanish. All you're left with is c1 there. And now this one here, derivative here, the 2 goes down, and then then this becomes a 1. So this becomes here. The 2 goes down here, c2 x minus a power of 1. Likewise, in x1, the 3 goes down, and then this subtracts a power, goes to 2, and you get the c3x minus a, etc. And this is equal to, and you can see the derivative here, so this n goes down, you subtract 1. So this is the summation n equals 0, from n equals 0 to infinity of Cn x minus a, to the power of n. And now this becomes over here, it just becomes the summation from n equals 1 up to infinity of n Cn x minus a to the power of n minus 1. Again, just a basic derivative rule. This goes down, the n goes down, subtract by 1. And we start from n equals 1 because, well, n equals 0 is vanished, so you could just ignore that. You could even put n equals 0, it doesn't change anything. Except, actually, no, if you put n equals 0, then this would be a negative power. So that's this is actually n equals 1 to match up with this. So that this is n minus 1. 1 minus 1 is the power of 0. So this would be x minus a to the power of 0, which equals 1 over there. Alright, so that is a derivative, and yeah, so that is how you differentiate it. You can just differentiate it just like a typical function, so the terms inside differentiate. And likewise, the integral, you can also do the same thing. Yeah, so if this is a function, now if you take the integral of it, if you take the integral right here, so c1 is a constant, the integral of that, actually no, not c1, we're dealing with this, not this one. That's a derivative, so c0 integral of that, that's just going to be, well, you add c0 is going to be x there, then plus a constant c. But they've rewritten it like this, and I'll get to that in a bit. I'll also just show that right here. So in part II, the integral of c0 dx is equal to c0x. Yeah, so integral of constant goes to x, and then plus an extra constant, they'll call it c1, is written as, so they wrote it like this. Yeah, so they wrote it as this c plus c0 times x minus a. So there's a plus c there, where the c without the subscript is equal to c1 plus a C0, and again, these are just a constant, so just writing the constant in this way as a function of the C0 there. And this is just so all the terms of the series have the same form, so that you write it as a C0 x minus a. So anyway, so that's the that term. Then the next ones are pretty straightforward. So you have the C1 times x minus a. So the integral goes to a 2, then divide by 2. There's a 2, and there's divide by 2. The next one's going to be, this would be a 3 divided by 3, like that. Again, just remembering the integral rules there. So then what this ends up being, if you write it in this formula form, equals to c plus the summation from n equals 0 to infinity of cn, and then x minus a to the power of n plus 1, and then divided by n plus 1. Yeah, so if this is n right here, and then this would be n plus 1, then divided by, then yes, then this would go to n plus 1, divided by n plus 1. When you take the integral and you do this for all the term. And the 0 is c0 there, when you plug in n is 0, that just goes to 1, and divided by 1. And in both cases, you're asked for the radius of convergence for the derivative and the integral. Recall that the radii of convergence of the power series in equations 1 and 2 are both r. So they're both the same. So they don't actually change. So it's the same as the function f, like that. Very interesting. And yeah, that's this form right here. This is just taking the integral and derivative, but in more generally. So note 1, equations 1 and 2 in theorem can be rewritten in this form, just so it's more straightforward as opposed to actually evaluating this integral. So this part that you could write this as a formula 3. So d over dx of, so derivative of the series, of the power series, summation from n equals 0 to infinity of cn x minus a, the power of n, is equal to the derivative inside, like that. Yeah, so the derivative of the series is equal to the summation of the derivative of every single term. So d over dx of the terms inside cn x minus a, the power of n. And likewise, the integral of the entire series, the integral of the summation from n equals 0 to infinity of cn times x minus a to the power of n dx, is equal to the summation from n equals 0 to infinity of the integral of every single term. So the integral of cn x minus a to the power of n dx. So yes, very, very fascinating stuff like that. And just for reference and for recap on that earlier video. So we know that, here's some more notes. So we know that for finite sums, the derivative of a sum is the sum of the derivatives, and the integral of a sum is the sum of integrals. Equations 3 and 4 assert that the same is true for infinite sums. So this one's usually the case for regular finite sums, but now we're looking at infinite sums. So the same as, so these equations assert that is true for infinite sums, provided we are dealing with a power series. For other types of series of functions, the situation is not as simple, and this is exercise 36. I believe I went over that in this video. And note 2, although theorem 2, this theorem 2 right there, states that the radius of convergence remains the same when a power series is differentiated or integrated, this does not mean that the interval of convergence remains the same. Remember, at the endpoints, it could be an open or closed bracket, so the endpoints may not be. So it may happen that the original series converges at an endpoint, whereas the differentiated series diverges there. So that's the exercise 37. And another note here, note 3, the idea of differentiating a power series term by term is the basis for a powerful method for solving differential equations. We will discuss this in method, this method in chapter 17, or in this case, a later video, which will be on second order differential equations, and I'll be in the future. Hopefully we get to that soon. Alright, so that is basically the integrating and differentiating power series.